There are minerals literally all over Earth, but sometimes they turn out super pretty and they're classified as gemstones. So, how is it that gemstones form? Why do they end up so beautiful? In this video, I'm going to be talking about how igneous and metamorphic gemstones form. I'll talk later about what those terms mean and why they're different from sedimentary and sometimes even hydrothermal gemstones, which the line there gets a little fuzzy between metamorphic, hydrothermal, and sedimentary, but I'll talk about that later. And I will have a separate video about the other types of gemstones. First off, what are gemstones? Well, they are minerals, rocks, or organic materials that possess exceptional beauty, rarity, and durability, making them valuable. They're often used for jewelry, decor, and sometimes even industrial purposes. They exhibit a range of colors, transparency, luster, and optical properties. And like I mentioned, gemstones can form through processes like igneous and metamorphic ones, which just mean the crystallization of melted rock in the case of igneous processes, and metamorphic ones form by putting rocks or minerals that have already formed under intense heat and pressure to transform them into something new. However, like I mentioned, some gemstones do form in sedimentary environments, and therefore gemstones can basically be found in various environments around the world. There isn't just one or a couple environments in which gemstones form. They form in many different environments. So igneous gemstones form when magma or molten rock cools slowly to form large, well-defined crystals. I'll talk more about this when I get to the specific example section of this video. And metamorphic gemstones form when pre-existing rocks are subjected to high temperature and pressures, causing the minerals to transform. I'll also give specific examples of this. And I do want to mention before we move on that there is a fuzzy line between hydrothermal and metamorphic gemstones because technically hydrothermal alteration or the alteration of host rocks by hydrothermal solutions, hot mineral rich solutions, is a type of low pressure, low grade metamorphism, but it does hinge on the side of sedimentary when we get to the types of silicon dioxide minerals that precipitate directly from the hydrothermal solutions. All of those fancy words just mean minerals that come out of that solution, crystallize from that hot mineral rich water solution. Those I kind of distinguish from metamorphic ones because it's not the host rock that's transforming due to the high temperatures and high pressures. Rather, they're crystals that are forming directly from the mineral rich solution. So I have a whole separate video where I'll talk about sedimentary gemstones and hydrothermal precipitates that we also classify as gemstones, which will be kind of the second part to this one. But I do want to emphasize here that this distinction is fuzzy, and I'm only doing this to try and separate the videos equally so neither of the videos are too long. It's not that this is an official distinction because hydrothermal alteration is technically metamorphism. So getting to the specific examples for this video, we will talk about diamond, ruby, sapphire, tourmaline, emerald, aquamarine, garnet, peridot, jade, topaz, lapis lazuli, and turquoise. And for the next video, we will go over opal, citrine, amethyst, pearl, moonstone, onyx, coral, and amber. So that's kind of, like I mentioned, the distinction I make between igneous metamorphic versus sedimentary and hydrothermal. But again, not an official distinction, just so I had a relatively equal amount of gems to go over for each video. And also note that this list is not complete. I just didn't have time to discuss all gemstones ever. So if you don't see your favorite on either of these lists, please comment it down below and maybe I can make a future video about that and others that I didn't go over here. First and foremost, we must discuss diamonds. Everybody loves diamonds. Diamonds are made of carbon. They form deep within Earth's mantle under intense heat and pressure. Where they get their carbon from is typically organic matter, carbonates, and carbon-rich minerals, which can become buried and taken way down deep into Earth. And this is where the diamonds form from the carbon-rich material. There's actually a specific diamond stability zone where diamonds typically form around 150 to 200 kilometers depth in Earth's upper mantle. And I did see some papers that discussed much deeper mantle diamond zones, but this is the typical one that people talk about when they talk about the stability zone of diamonds and Earth. And the pressure required for diamond formation is typically 45 to 60,000 times atmospheric pressure at sea level. And the temperature is typically over 900 degrees Celsius or 1,650 degrees Fahrenheit. Sorry, that C is supposed to be an F. And the carbon typically enters the mantle through subduction. And then the high temperature and pressure conditions within the mantle in the stability zone of diamonds causes the carbon atoms to form covalent bonds with one another and become tightly packed into a crystal lattice. Covalent bonds, if you don't know, are the strongest bond type. So they form these really, really strong bonds, which is part of the reason diamond is so hard and durable. It is a 10 on Mohs hardness scale, and that's the hardest you get. And diamonds are brought to Earth's surface by volcanic eruptions or magmatic intrusions of kimberlite or lamproite pipes. This is just a type of peridotite, an ultramafic type of volcanism that brings deep, undifferentiated mantle material to Earth's surface. And this is where you could get uplift of diamonds to Earth's surface, where we can actually mine for them. And because diamonds are so hard, like I mentioned, they don't really weather or erode very easily, obviously, and thus can be mined from alluvial or fluvial materials or their original volcanic deposits. So they can undergo transport and erosion, but they're still there. They don't weather easily. Also, note that ultramafic eruptions, which ultramafic is just an igneous term used to describe magmas or igneous rocks that are relatively silica poor, and ultramafic volcanism was more common on early Earth because on early Earth the mantle was less differentiated. Over time it differentiated by density, bringing less dense, more silica-rich magma to the surface parts or the upper parts of the mantle and crust, and leaving silica poor, ferromagnesian-rich minerals deeper in Earth's interior. And I talk a lot more about mantle differentiation and ultramafic volcanism and what it means in my Io videos, the videos I have about Io, which is the volcanic moon of Jupiter, because Io might have current ultramafic volcanism going on it, which might tell us a lot about the mantle composition. So long story short, ultramafic eruptions are rare on modern Earth because it has been differentiated over time, and more silica-rich eruptions, so mafic to felsic material, tends to be, what volcanoes erupt these days. I do really quick, before moving on to the next gemstone, want to talk about diamond color, because I was under the impression that most diamonds were clear and any type of faint color might be due to impurities, but that's not always the case. Diamonds can be pretty much apparently any color in the rainbow, but this is rare and typically faint. The colors can result from impurities, like I thought, like white, yellow, and blue diamonds result from impurities of nitrogen, hydrogen, chromium, nickel, and boron, and different combinations of those elements. Or color can result from crystal lattice deformation due to super intense temperature and pressure. So on its own, the carbon lattice of diamonds is colorless. It is clear. It is transparent. However, with the elemental impurities I just mentioned, it can be different colors like white, yellow, and blue. But if the carbon crystal lattice is deformed in some way, then it can cause light to refract and reflect differently to the point that it shows or appears a different color, like, for example, brown, red, or pink. And there are also green diamonds, which are caused by radiation from uranium decay deep within the mantle, which is crazy. Basically, this radiation from uranium decay causes carbon atoms to get knocked out of the lattice, creating vacancies, lattice deformities, that lead to different absorption properties, light absorption properties, and thus color. I should mention, if you're not aware, that color of things like minerals is just the light that's getting reflected and hitting our eyes and transmitted. All the colors that it's not are the ones that are absorbed, if that makes any sense. Anyway, green diamonds are pretty cool, and they're the only color of diamonds that can be synthesized, that can be kind of recreated by us. The others, however, the other colors of diamonds have to occur naturally, and we cannot recreate their conditions of formation at Earth's surface, at least not for a reasonable cost. Next, we have rubies and sapphires. Rubies and sapphires are actually the same composition, which is why I'm combining them into these next few slides, and their composition is aluminum oxide. This is actually a mineral called corundum, and ruby and sapphire are both just varieties, different colored varieties of the mineral corundum. It's actually the second hardest natural gemstone after diamond. Rubies and sapphires formed by both igneous and metamorphic processes. Their igneous formation starts with magma that's rich in aluminum and trace elements like iron, titanium, chromium, and vanadium in the mantle or crust. And as the aluminum-rich magma rises and cools, corundum, aluminum oxide from the aluminum-rich magma, begins to crystallize from the magma, and traces of iron and titanium incorporated into crystalline corundum result in blue sapphire, whereas if chromium is incorporated into the crystalline corundum, it forms red ruby. Again, this is an example of elemental impurities that cause different colors. I can actually make a whole video about why typically transition metals are the cause of colors in minerals. If you want that, comment down below. It has to do with like their electron configuration and the way it like jumps when light hits it. Metals create the coolest colors. I get to work with dissolved molybdenum in the lab, and it's like this bright orange sometimes, and sometimes it's dark red. It's very cool, very fun. Anyway, I can talk about that in another video if you want me to. So comment that down below if you would like that. So that's their igneous formation, and their metamorphic formation starts with a source rock, such as basalt containing corundum, aluminum oxide, and trace amounts of chromium, iron, and/or titanium. Ruby forms during metamorphism if the chromium-rich minerals in the source rock, like chromite, for example, react with aluminum and oxygen to form corundum with chromium impurities. And sapphire can form basically by the same general process, but involving iron and titanium impurities reacting with aluminum oxides instead of chromium. Next, we have tourmaline. Tourmaline is like such a beautiful mineral. I love tourmaline. It's not a mineral. It's actually has a variety of varieties within the group of tourmaline minerals, and they occur in a wide range of colors. Tourmaline can also form by either igneous or metamorphic processes. It can also form when hydrothermal solutions, hot mineral-rich fluids, circulate through fractures or pores in rocks and deposit minerals as they cool. And tourmaline formation often starts with source rocks that contain boron, aluminum, silicon, and various other elements, such as granite or pegmatites, which need a whole slide to themselves. So what are pegmatites? Well, pegmatites are igneous rocks with exceptionally large crystals, from several centimeters to meters in diameter. Pegmatites generally form from the last part of a magma body that crystallizes. This fraction is basically highly enriched in volatiles and trace elements, and volatiles such as water lower the viscosity of this melt fraction, promoting rapid diffusion of molecules through the fluid and enhancing crystal growth rates, allowing very large crystals to grow. Now, I said a lot of fancy words there. I want to kind of break this down. So basically, large crystals and igneous rocks form when slow crystallization takes place in a melt or like magma chamber. The reason slower crystallization leads to larger crystals is because ions have to diffuse to a nucleation site in order to form a crystal. In other words, ions have to have time to travel through the melt to get to the nucleation site of that crystal grain to form larger crystals. If they have time to do so, if the melt is cooling slowly, then larger crystals form because there's fewer nucleation sites with more time for ions to diffuse to them. Whereas if a melt cools very quickly, for example, if volcanism occurs and the magma is exploded out of a volcano, all of that has to cool really fast because that's on Earth's surface where it's way cooler than within Earth. The slow cooling only happens within Earth, just shallow enough to cause it to crystallize, but not quickly. So when it comes out and is at Earth's surface, and like you see a lava flow cooling, that's cooling really quickly, almost instantaneously, to the point that all the grains crystallize right where they are. In other words, all the ions form nucleation sites right where they are. So they're tiny crystal grains, and there's more of them. Whereas when magma cools slowly, there's large crystal grains and there's less of them. So I hope that makes sense. Anyway, the lowering of the viscosity promotes rapid diffusion of the ions to the nucleation sites and promotes more rapid crystal growth. And water also lowers the melting temperature of magma and thus promotes the slower cooling of that magma body. So it increases the crystal growth rate and slowers the cooling, leading to even larger crystals to form. And this is how pegmatites form. The slow growth of tourmaline allows crystals to become extremely large and typically prismatic in crystal habit. Various impurities present during crystal growth give rise to different colors, such as iron-rich tourmalines that tend to be black, and manganese, chromium, and vanadium create green, pink, blue, and red tourmaline. My favorite variety of tourmaline is watermelon tourmaline, which is due to a combination of aluminum, boron, iron, magnesium, manganese, lithium, silicon, and fluorine. Next, we have emerald and aquamarine. Emerald and aquamarine are both varieties of beryl, which is a beryllium aluminum silicon oxide mineral, but they differ in color. Emerald is typically a green or emerald color, and aquamarine is also kind of what it sounds like. It's a lightish blue color. Beryl forms typically in pegmatites like tourmaline. Basically, that just means late stage, slow cooling magma enriched in beryllium and aluminum. And trace amounts of chromium and vanadium incorporated during crystallization make emerald green, whereas trace amounts of iron make aquamarine pale blue. Now, I do want to stop here for a second and mention that you may have noticed that iron, especially, and chromium and vanadium, all of these metals cause different colors in different crystal lattices. Whenever I was in igneous petrology, I would be like, okay, so this thing causes pink color. And I would think that's the only thing it would ever cause, no matter what the mineral was. But that's not the case. The same impurity can cause different colors in different mineral lattices. The reason being is because each mineral lattice has a different, structure. Emerald and aquamarine, in other words, beryl, has a different mineral lattice structure than tourmaline. So iron causes tourmaline to be black typically, whereas iron causes, beryl to be blue, aquamarine. And the reason this is because structural changes change the way light interacts with that thing. So when the mineral has a different lattice structure, it has different light absorption and reflection properties. Another reason that iron sometimes causes different colors in different minerals is because they can have different what are called oxidation states. In other words, they can have different numbers of electrons in whatever mineral they're in as an impurity, and their different oxidation states lead to different colors. Next, we have garnet. Garnet has a variety of formulas depending on what ions it includes. There's just so many different garnet varieties that we can't even make a formula with one, type of ion here. We had to put X or Y. X in this formula is typically either calcium, iron 2 plus, manganese, or magnesium, while Y is typically aluminum, chromium, or iron 3 plus. Garnet is a group of silicates. Whenever there's a silicon and an oxygen at the end of a mineral formula, that's called a silicate mineral. And it's a group of these that includes many varieties or colors of garnets, and it typically is metamorphic. Protoliths, or parent rocks, original rocks of the eventual metamorphic garnet product, include things like shale, basalt, and granite, as well as other rock types. Garnet can form from a lot of different rock types. As long as they have any combination of these elements, They can have the potential to form garnet if they undergo the right metamorphic conditions. In other words, reach a high enough pressure and temperature, but also not too high. I talk more in my metamorphic petrology videos about how different minerals form under different metamorphic grades or temperature and pressure conditions. So the high temperature and pressure of metamorphism causes minerals in the protolith rock, the original rock, to undergo chemical and structural transformation and rearrangement. Aluminum and silicate are essential components of garnet and are derived from the protolith from original minerals like feldspars and micas, common in things like granites and shales, and garnet forms during solid state diffusion during metamorphism. This just means that ions migrate in the solid matrix of the rock to form new minerals. In other words, it doesn't melt completely. If it did, it would recrystallize and then be classified as igneous, not metamorphic. So it's still technically a solid, but it's under such high temperature and pressure that allows certain ions to migrate. And this is called solid state diffusion. And this is why some of the minerals like feldspars and micas can undergo transformation and their ions can kind of combine or react in some ways to form different garnet varieties. And the garnet varieties or colors are just dependent on the available trace ions, trace elements. For example, almandine is a variety of garnet that is typically red, brown, or purplish due to iron impurities. Again, iron is one of those common impurities without a common cause. It causes many different colors depending on its oxidation state in the mineral and the mineral structure, as well as other impurities. For example, pyrope is typically a deep red due to both iron and manganese impurities. So the additional presence of other impurities can cause iron's effect to be different. Spessartine is another variety of garnet that is typically a red or orange color due to manganese impurities. And grossular can be green, yellow, brown, and sometimes even red due to a mixture of chromium, iron and manganese impurities, respectively. Now moving to peridot. Peridot is a variety of olivine, and the source rock for olivine, and by extension peridot, is peridotite. So this one's kind of named very conveniently. Peridotite is an ultramafic igneous upper mantle rock, and mantle peridotite is composed largely of olivine, which is a ferromagnesian or iron and magnesium silicate, which is often a yellowish greenish color. Whenever I was taking igneous and metamorphic petrology, I would remember my mom's saying, which is all that's green is olivine. She's also a geologist, if you couldn't tell. So basically, volcanic activity brings this upper mantle peridotite-rich magma to Earth's surface, and cooling and crystallization occurs as the magma rises because temperature lowers as it gets closer to the surface and things start to crystallize. The peridotite crystals grow as the magma cools, and because olivine, and by extension peridot, starts to crystallize at higher temperatures relative to other minerals in the magma mixture, they crystallize out of the magma first, and because of their really high density, they sink to the bottom of the magma chamber. They're also often allowed to form larger crystals because they have a longer time to cool, since they start to crystallize sooner than the other things in the magma chamber, and thus at a deeper depth in Earth's crust. And peridot is often found within peridotite or kimberlite or even sometimes basalt. Now, peridot and olivine in general rapidly alters to clay and iron oxide in the presence of water and air due to oxidative weathering. Thus, sometimes it can be mined from alluvial deposits, but more often from its original volcanic deposits, because if it's, transported or eroded or weathered any further from its original deposits, it might as well just be completely altered and, no longer peridot. Note again that peridot formation requires specific conditions, crystallization of olivine-rich ultramafic magma, which are relatively rare, and this makes peridot pretty rare. Next, we'll talk about jade. Jade consists of two minerals, jadeite and nephrite. This is why when I talked about what are gemstones at the beginning of the video, I didn't just say minerals, I also said rocks, because jade is actually technically a rock, not a mineral, because it has two different minerals. It can be green due to chromium, pink, lavender, or purple due to manganese impurities, yellow, orange, or reddish, or brown due to different valencies of iron. This is kind of similar to saying different oxidation states of iron, like I had mentioned earlier. Or it can be gray or black due to graphite impurities. So All these different impurities within the jadeite-nephrite mixture can cause it to be different colors. And the formation of jade is often associated with regional metamorphism. So, like I have mentioned in my metamorphic petrology playlist, there are different types of metamorphism. Regional metamorphism is kind of this large-scale metamorphism at plate boundaries. So there's tectonic plates, they bump into each other. Sometimes an oceanic plate subducts under another oceanic plate or continental plate. And where subduction occurs, you get this huge regional scale metamorphism where the continental plate and the oceanic plate are pushing up against each other, and you've got huge pressures throughout the entire region. It also creates high temperatures, and there's melting, and there's igneous activity because of this, and all around the igneous activity, there's contact metamorphism right where the magma chambers touch or come in contact with the host rocks in there. And all around that, where there's really high pressures at the plate boundary, there's regional metamorphism. Hydrothermal fluids, rich in silica and other minerals, infiltrate the rock, facilitating the transformation of original minerals into jadeite or nephrite. So basically, these subducting plates tend to bring down with them water either within pore spaces of rocks that are buried in the ocean basin, or hydrated minerals that eventually get to a depth and a temperature where they dehydrate and the water is released, which contributes to both melting of mantle and crust material that leads to volcanism, but also contributes to hydrothermal alteration of the solid host rocks by dissolving some and reprecipitating and altering others. Now moving to topaz. Topaz can be blue, yellow, purplish, pink, and clear or whitish, kind of opaque, and it commonly forms in igneous rocks, particularly those rich in aluminum and iron, like granite, pegmatites, or rhyolites. Hydrothermal solutions, again, hot mineral-rich fluids, can circulate through fractures, dissolving existing minerals and depositing new ones, like topaz. Trace impurities such as iron, manganese, and chromium, irradiation, and heat treatment can all three cause the color of topaz to change. Now moving to lapis lazuli, this is primarily composed of lazurite, which is a mineral with this huge long formula, but it also has other secondary minerals in it, but this is the main component is lazurite. And basically lazurite forms when magma intrudes into limestone or marble rich in diopside, which is a magnesium calcium silicate mineral. So remember that when magma intrudes into pre-existing rocks, it can cause contact metamorphism to whatever those rocks are that are in contact with the magma chamber. And this is higher grade, closer to the magma chamber, and then it gets a lower grade metamorphism out of the magma chamber. But it is low pressure, it's just high temperature. And so things like limestone can transform into marble, can be metamorphosed into marble due to contact metamorphism. And this can then be subject to hydrothermal alteration when sulfur-rich fluids are released from the magma and interact with the limestone or marble to deposit pyrite, an iron sulfur mineral, and lazurite in the voids and fractures of the rock. Oftentimes, because these two minerals are typically associated with one another due to the sulfur-rich fluids that form pyrite in association with lazurite, the gold and pyrite inclusions, pyrite, by the way, is just fool's gold, so its inclusions are often this golden color, and these inclusions within lapis lazuli often add sparkle and contrast to make it kind of shimmer in a way. Next, we have turquoise. Turquoise is this long copper aluminum phosphate hydroxide hydrated compound here that forms as a secondary mineral in a host rock like granite, limestone, or sandstone. Copper, aluminum, and phosphate from copper, aluminum, and phosphorus-bearing minerals in the host rock are carried by hydrothermal fluids that infiltrate fractures and pores in rock. Again, this hydrothermal process is very similar to the others we've already discussed in this video, where basically these ions, in the case of turquoise, the copper, aluminum, and phosphorus ions, and phosphate ions, are carried by hydrothermal fluids within fractures and pores in rocks, and it precipitates out or deposits out of the solution as turquoise. And in terms of turquoise's color, its greenish blue color is caused by copper, but it's in part caused also by phosphorus. phosphate, which I didn't know before making this video. As the chemical reactions within the hydrothermal fluid progress, original minerals in the host rock are replaced by turquoise. After the initial formation, turquoise can continue to undergo alteration and transformation when exposed to water and air. The ongoing reaction with water and air can affect the stability, color, and texture of turquoise over time. If you've ever been kind of hunting for turquoise, I have, and you've ever seen natural rough turquoise in the field, it typically doesn't look anything like its polished counterparts. Kind of looks like this rusty, sometimes occasionally blue-ish green, I don't know, rock. It doesn't look all that pretty. Even this picture here is like better than what I've seen. But when it is, you know, polished, if you find nice big chunks of it and can polish it down, it is quite beautiful. So those are all the gemstones that I'm going to talk about in this video. Like I mentioned, I'm doing a part 2 to this video where I will talk about more low temp, low pressure, sedimentary almost gemstones. Some are absolutely sedimentary, like pearls, amber, but then some of them are a little bit more fuzzy and potentially metamorphic, more like hydrothermal ones like we talked about in this video. Things like opal, amethyst, citrine, basically all the varieties of silicon dioxide or silica. And so if you want to hear about any of those gemstones, come back for that video. I will link it up here if it's out by now. And as always, my references are linked down in the description box below. And I can't wait to see you guys next time. Bye.